because we had to adjust the schedule a bit in light of the global town hall that is occurring in 2 hours and 15 minutes from now. So as a result, what we've done, if you were here yesterday, I've communicated this yesterday, but just in case, we're moving everybody up 15 minutes. So if you see on this slide that you were starting at 7, Meredith, you will be starting now, okay? And then so on and so forth. If you go to the next slide, just to remind everyone, the ground rules. So you've heard this in other meetings, the other days. This information today is for internal use only. Please turn off your microphone, do not record. Please do ask questions via chat. I think there's a lot of energy that's happening in the chat. I know that the presenters really appreciate that. It lets them know that this was a valuable topic and that you're interested. Leverage the react button. I think that's worked really well. It's great. It's great to see all the hands and applause and hearts go up. It really, again, tells the speakers, even in a virtual environment, that this is resonating. And then be sure to thank all the presenters. A lot of work went into this on their end, and I think there's been some valuable connections already. So with that, I am going to turn it over to Frank.
Yeah. Okay, thanks, Phil, for introduction. So this morning we'll start off with 1 hour talk about APM. The process we have in APM is that we start with a gas, ethylene, and we make ultra high molecular weight polyethylene out of that. So one of the presentations today is being done by John. John will tell more about the ultra high molecular weight research which we are doing. The powder is being used to make the fiber in a spinning process. The fiber is serving multiple markets, and as you see on this slide on the right hand side, we serve the rope market. Judith will give a short presentation on that one. The ballistic market, which is also very important for us. Hans and Raoul will give a bit of short presentation focusing on flame retardancy in ballistic composites. Last but not least, also in the fabrics and composite side, we are having some nice examples of market launches based on our innovation, and that's where we're going to start today. So Meredith will start off with a short presentation on composite fabrics. Don't want to take too much time of Meredith, so Meredith, floor is yours. Meredith is in, or?
Meredith, if you're on mute.
Can you?
We heard you for a second, Meredith.
Am I back, and can you hear me?
You're back, and we can hear you.
Yeah.
Great.
Great.
Okay. So yeah, this talk will be maybe a little different from the rest you've heard over the last couple days, and a bit shorter. But partially because at Dyneema, at our core, we're not really formulators. So our value proposition is not so much in what additive package we can offer to solve a customer problem. Instead, we're essentially a brand based on a technology platform. So although in markets where we're already well established, we do innovation based on market pull, and we develop products based on deep understanding of customer needs. But generally, the way we grow into new markets is to do some amount of tech push. And we look for new areas where what are tech.
Meredith is freezing.
This slide is okay. And I was kind of expecting that wolf packs were a little smaller. I didn't think there'd be like almost 300 wolves. But this is great. This is even better than I'd hoped, because what I really want to do here is share an idea and see if you can help me find new markets where this idea could get traction. So the more of you, the better. Okay, so starting off with this slide, at Avient Protective Materials, one of the platforms that we're looking to grow is based on Dyneema composite fabrics. And these are ultralight composite sheets based on our Dyneema ultra-high molecular weight PE fiber, protected by a face film on both sides. And we make these so thin that they're intrinsically flexible, and they can function like a fabric, even though their fibers are topologically unidirectional, and they're not interwoven as in a typical fabric. And these were originally developed as Cuban fiber by the Cubic Tech Corporation in Arizona. And they initially were designed as kind of a high performance sailcloth material. For example, for the America's Cup, using lightweight unidirectional sheets that could be laid up in a custom way according to the needs of a specific sail. And over the years, it's found various other applications. A major category for us being in ultralight outdoor gear, for example, tents, where we're able to make a material which is intrinsically waterproof due to the films that we use. It doesn't sag because our Dyneema doesn't expand when it gets wet. And we do this all for less than about 20 grams per square meter for the final fabric. So if you look in the ultralight backpacking community, this material really dominates. But we're looking to expand into adjacent markets. On one hand, by adding new functionality, and on the other, by bringing down the cost. So a straight way for us to add new functionality is by just changing the face film. For example, using a woven fabric as one of the face films, we can bring a lot of abrasion resistance to the product, which is the basis of the materials that we use in ultralight backpacks. So another emerging market for us that we're looking to expand into is in inflatables applications, broadly speaking. And what do I mean by inflatables? Generally, any lighter than air balloon or other inflatable structure that could carry a payload of some kind. Now, you may remember one particular spy balloon that made a lot of noise a couple years back. So generally, that could be one example. But you should also think about not just one, but even clusters of balloons that could be deployed rapidly, either individually or as a whole group, to quickly provide coverage over an area for whatever purpose. Or beyond that, and this is the example that's pictured on the upper part of the slide, you could think about high altitude platforms that could carry payloads all the way up into the stratosphere for longer periods of time and fulfill some of the needs that satellites provide today. So long story short, we're looking into developing materials for these and other applications. I can have the next slide, please. All right, so the core technology that underpins this platform, the reason we're able to produce such lightweight materials is actually not so much the Dyneema yarn itself that we use, but rather it's a unique fiber spreading process where we take a bobbin of yarn, which is a bundle containing hundreds of little filaments, and we can spread this out to be less than 1 filament thick if we want to. So if you look really closely at the composite fabric, you can see that actually the individual filaments all lined up. So again, I start off with a tow of over 100 filaments, go through this fiber spreading process, and you can see in this example, after spreading, there are little trains of individual filaments with a gap in between. So this is an example of what our lightest grades look like, and this is what allows us to be lighter than woven fabrics, because we're able to spread our yarn all the way down to really low aerial densities without needing to rely on a fine denier yarn to get that. Now, in our heavier grades, quote unquote heavy, we make essentially a monolayer of filaments. And because we're under the Dyneema brand, we use this with Dyneema yarn, generally in applications where lightweight strength is critical. But although it may not fit nicely in our brand story, there's really no reason that it needs to be a Dyneema yarn, right? We could spread other untwisted yarns. So my question to you is, can you help me think of any other areas where Avient might be able to leverage this? And so next slide, please. Right, so I've only so far shown you applications that use a form factor like a fabric, but there's no reason to limit yourself to fabrics. It could be some other form factor. Even staying in 2D, you could think of this as a general way to reinforce a film, which is maybe too weak to do whatever it needs to do. So in other words, it could function like a scrim to reinforce a film. Or if you want to think in 1D, you could use this as a unidirectional tape. And maybe you could take that tape and wrap it into a 3-dimensional shape, etc. It also doesn't need to be in lightweight applications. You could also use this in a conventional composite if you needed to minimize the ply thickness in order to achieve some kind of performance benefit. Or even in general, if you're making any kind of unidirectional composite and you're having trouble with toe spreading, this could be a way to improve the quality of your product. So again, open question to you, could you use this? Could your friends use this? Can you think of any applications or areas where this might come in handy? And if so, please reach out and let's have a conversation. And yeah, that's my last slide. Thank you.
Well, thanks a lot, Meredith, and yeah, thanks for having the invitation to all of us to think about this. Like Ashish said, and the sum of the whole should be bigger. The whole should be bigger than the sum of the parts, and I think that is also an example where we really try to leverage all the knowledge which we're having in Avient for especially in the field of composites. Thanks for that. We move to Judith. Judith is one of our experts in oh no, sorry, we go to Raoul and Hans first on the fire resistance for ballistic armor. So Hans, I think you start off.
Yes. Okay, I'm doing this presentation together with Raoul. Raoul is member of the innovation team. I'm part of the marketing and sales team. And we will tell you about the efforts we have done to increase the fire resistance for ballistic armor based on Dyneema. Next slide, please. I will have a short talk about what is Dyneema and also the need for the fire, smoke, and toxicity properties that we see in the market. And Raoul will introduce you the 2 routes that we have explored to improve those properties, resistance against fire and smoke. And in the end, we come with short conclusions. Next slide, please. And Dyneema, as also Meredith said, it's a fiber made of ultra-high molecular weight polyethylene. It's 15 times stronger than steel, and still it's light enough to float on water. With this fiber, we make also so-called unidirectional sheets. You see here the fibers put parallel next to each other. There is a resin included to keep those fibers together. And we add other layers of fiber perpendicular to the first one. And that's how we make a UD. And we sell that on big rolls. Our customer make then the armor panels out of it by consolidating in a press. Next slide, please. Here you see some examples of hard ballistic armor and soft ballistic armor. In the left, you see that one of our customers have sold over more than 1 million vests to the US law enforcement community. And on the right side, you see an example of a shield. And this shield has been used and saved lives in the Bataclan events in Paris in 2015. Next slide, please. What you see in platform armor is that there is typically requirements on fire, smoke, and toxicity. There are various standards used for these type of aspects. We can map a few of those, which is a vertical flame test with our material. And mostly armor manufacturers use add-ons like protective layers or functional coatings to pass their test. That could also be glass fiber or adamant fiber-based fabrics. The perception in the market, and especially in the end user market, is that Dyneema is easy to burn. And we are looking into improvements in our materials to have better resistance against fire or smoke and toxicity. Next slide.
Okay, so I take it over. So yeah, we have some ideas how to render Dyneema composite flame retardant. But before we can do that, we have to realize that the flammability of polyethylene is determined by its high rate of thermal degradation and high heat of combustion, which is one of the highest amongst many synthetic polymers. You see there on the left a plot of the thermal degradation where you have the mass and the rate of mass loss as a function of temperature. And in comparison to other relevant polymers using this type of application, polyethylene has a very high thermal stability, meaning that it needs a very high temperature to produce enough products of degradations in the gas phase that can ignite. Yeah, but if it ignites, the rate of degradation is so high, yeah, that it burns. When it burns very fiercely. And this high rate of degradation, combined with the high heat of combustion, makes it very easy for polyethylene, much easier than the other polymers, for polyethylene to burn and self-sustain its own combustion cycle. And it also makes it very difficult to self-extinguish. And the self-extinguishing ability is much desired in many of the flammability tests that Hans mentioned before, which are relevant for the application that we are targeting. Next slide, please. So that's why for Dyneema composites, we need a flame retardancy approach that first take advantage of the high thermal stabilities, this resistance to ignition of which is intrinsic to polyethylene, to delay or even suppress totally ignition in the application. And if ignition happens, then the material is burning. Well, we need to promote some formation of some sort of barrier, protective barrier, that reduces the rate of thermal degradation and reduces burning time. We explored two routes to make Dyneema flame retardant composite. The first route at the top is at product level, so where we ourselves add a flame retardant additive to the matrix that we use to make the composites. So what you see there in the picture, this approach has the lowest impact on weight of the composite. And the route two is where we call it an application level route. In this case, our customers will have to either apply a flame retardant as a finish coating, for instance, using an ambient geopolymer coating. Yeah, this will be need to be applied to already consolidated panels. Yeah? Or a second possibility is that customers make hybrids of Dyneema composite sheets with a glass fiber reinforced PET composite made by Avient, which contains a flame retardant as well. So by, for instance, alternating these layers and consolidating panels out of these layers. Next slide, please. So now I will show you some examples of what we have seen. Yeah, you see here the results of adding a flame retardant within the resin, so at product level. So this is a very harsh test we did. This is a so-called torch flame test. And you have there a sequence of pictures as a function of the testing time for two types of materials, without and with flame retardant. So without flame retardant is at the top, and you see that as soon as the torch and the flame makes contact with the composite catches quickly fire, burns with very tall flames, and it simply burns to the clamp. This is very bad. and you see that the material is melting and dripping, etc. All those things we don't want to see, and customers don't want to see. In contrast, when you are a flame retardant, this is the bottom pictures. There is some burning of the material, but it's very localized, and the sheets, every single sheet of this panel is forming a char, which helps to reduce the heat release and help the material to eventually self-extinguish. And a bonus in this case is that the ballistic properties of these panels are retained. Next slide. This is yet another example of the approach at application level. Here is where we applied geopolymer coating, finishing coating. And you see here again, two sequences of pictures, top and the bottom for Dyneema without any coating. Here you see essentially that, again, in this test, Dyneema without protection catches fire very quick. There is a very long after burning time. It needs to be blown out to put out the fire, and then you see how the panel looks at the end of the test, totally burned, destroyed, melt away. While the panel with the coating, you see here that it's very difficult to ignite. It doesn't ignite, and essentially nothing happens, and the integrity, mechanical integrity of this panel is preserved, and the test is passed. Next slide, please. Okay, this is a same test, but in this case, we hybridized the Dyneema material with a glass fiber flame retardant PET from Avient. We did this same type of test. Sequence of pictures as a function of burning time. Yeah? And you see that the material at the top row without flame retardant, surprisingly, this material didn't have after flame time, even after 60 seconds of the flame contact there. But you also see during the test that the material is much more exposed to the burner, and this makes it look not so good. On the contrary, the material with hybridized with a glass fiber flame retardant, you see that it won't catch fire as quickly, and there is at the contact of the burner this glowing effect that means that the material is radiating heat away from the flame contact, and this is the type of effects that we want to see and offers some protection against fire. So next slide. So concluding, we explored two routes, one at product level and the other at application level, and both are very effective and meet the requirements to pass the relevant FR tests. We are recommending a solution at product level because of wet gain reasons. We see that the surface protection of the Dyneema composites is essential to prevent ignition. And if the ignition doesn't happen, the material won't burn. And we are convinced that char formation in Dyneema panels, consolidated panels, will create a whole new perception and will change that perception that is out there about its flammability, smoke, and toxicity. That's it. Thank you.
Well, thanks, Raul, for the presentation, and Hans also for explaining the segment a bit. I see there are some questions all in the Q&A chat, so maybe good to also try to answer those. And Meredith, I see also a lot of remarks and questions regarding your presentation. I think we are still a bit ahead of time, which is good, I believe. So I would like to give the floor to Judith. Judith is one of our researchers for the marine and industrial fiber segment. So Judith, can you start your
Can you hear me?
Yeah.
Can you hear me?
Yeah.
Yes, we can.
Okay. Thanks. Yeah, and thanks for giving me the opportunity to present to this audience the interesting market developments for our subsegment marine and industrial fibers, and what we in innovation have been doing and need to continue doing to grow the segment. I said, my name is Judith Bos. I'm working as an application development manager in Avient Protective Materials. Next slide, please. An outline of the topics in my presentation. I will first give some insights in the customer base for applications for marine and industrial fibers. Then I will highlight the difference in requirements between the two biggest segments in Avient Protective Materials, marine and industrial fibers versus personal protection. Then why it's important for us to be back and forward integrated, and the engineering tools that we have been developing based on these principles. And in the end, the most important is how these engineering tools have helped and have been pivotal to certify and to get already the first commercial sales in mooring lines for floating offshore wind and crane ropes for deep water installation. Can we go to the next slide? Since I'm aware that not the full audience is familiar with our segment, I want to give an overview of the applications where we sell in and the form factors. So we sell fibers, and our customers make ropes, nets, slings, and synthetic chains from these fibers. And in these markets, we did a very good ingredient branding because they are often called Dyneema ropes, Dyneema nets, which makes that end users often think that we are the producers, while we are only the fiber supplier. Well, these products are sold in markets for heavy marine, so for vessel mooring in harbors. That is our biggest market, but also in slings for heavy lifting, nets for aquaculture, like salmon and sea bream farming. And one of the markets with higher brand recognitions is, for example, in yachting. Think of the Volvo Ocean Race, Olympic sailing, but also in synthetic chains for lashing and lifting. Probably all of you know the container ship Ever Given blocking the Suez Canal for 6 days. This salvage operation has been performed using also ropes with Dyneema. So you see that it's diverse markets with very different market dynamics. And go to the next slide. The biggest segment in APM is personal protection, which is mainly focusing on bulletproof applications. And as you understood from the presentations, and maybe already heard is that this requires really strength, because the moment that a projectile hits the vest or the helmet, it needs to have that strength. And this is different from for our marine industrial segment, because here the strength is needed over and over again with every lift, in every hour of vessel mooring, but also in the years for permanent mooring application. So the focus is really not on increasing and improving the strength, but it's really about durable performance in the application. We can go to the next slide. In order to get this durable performance, it's important to understand what is going on in a rope while being used in these applications. And we often refer to these failure mechanisms in simple terms of A, B, C, D, E, where A stands for abrasion, meaning the external abrasion. For example, when a rope is running over fairleads in vessel mooring. Bending is creating internal abrasion by friction in ropes. Creep is typical for high modulus polyethylene. It's elongation by sliding of the molecule with a constant load or a dynamic load, and then at a certain moment it breaks. And damage is mainly external damage from sharp edges or what have you. And the environmental conditions are related to the forces of nature. So UV, temperature, seawater, but also the surrounding of the where the rope is working. And sometimes there are detergents used, And the question is, how susceptible are our materials for that? To learn more on these failure modes, we need very deep application knowledge and understanding. We have to be out in the market, and based on that, we have built test equipment, which you see in the picture in the middle, where we try to simulate the relevant failure modes as close as possible to the real application. And I mentioned that we are not a rope supplier, but we actually can produce ropes, maximum 21-34 millimeter, and we can coat them, but that is for the purpose of really testing and weighing them. But we are also backwards integrated, being one of the only HMPE suppliers who produce our own raw materials, which makes that we can tweak them by copolymerization and give certain properties that make them suitable for the application, giving them long durability. And John will explain in the next presentation more about our capabilities there. And what I think is important to highlight is that these testing efforts are of course important to break, but that is really research. But in order to make the transition, we have to go from research to engineering. Research really looks into the number of breakage, cycles to breakage, how strong it is, and so on. While engineering is about preventing the breakage in the application and making sure to set up reasoning why it's safe and reliable to use Dyneema and in that specific application. And for this, we have developed engineering tools, the ones that are pictured on the right here and on the sheet. So we have a creep fatigue performance model, we have a bending fatigue performance model, a temperature, and a viscoelastic model. And this is not a one-time effort, it is continuously monitoring and learning from what we do in this application development in our global innovation centers, but also for market feedback. We are in close collaboration with our customers, but also with end users to get back ropes and slings from the market, where we perform what we call the rope CSI to improve our understanding. And these learnings we also again use to improve our models. And that is why you see, for example, not only creep fatigue 1, an improvement of creep fatigue 2 mentioned on this slide. Go to the next slide. Here you see 2 applications that I want to highlight further on in this presentation. Because these engineering tools have been very vital to these applications. And this is not something that our competitors are able to do. And the first one is being mooring ropes for floating offshore wind. Offshore wind is already an important segment using slings for lifting and installation of structures for fixed bottom. However, fixed bottom is limited to water depths of 50 to 60 meters. And if you want to go deeper, to deeper water depths, where often more wind is available, it's necessary to put the turbine on a floater. And of course, this floater needs to be moored with mooring lines to an anchor to the seabed in order to keep the station keeping, to keep it stable. In the next slides, I will explain how the engineering tools have helped with that. Another application is in offshore cranes, where we have been substituting steel cables. Yes. For mooring lines in floating offshore wind, the requirement is more than 25 years on lifetime. These mooring lines, these are under constant load, and creep is the Achilles heel for HMPE. So in HMPE, when there is a constant load, the molecules will start sliding along each other, causing an increase in length until breakage occurs. And we managed to improve these creep properties by a factor of at least 50 versus a standard HDP, high modulus polyethylene by copolymerization. Therefore, creating what we call molecular anchors to limit the sliding of these molecules. And that is only possible because we are backwards integrated. These performances were tested by our labs and turned into engineering tools to predict the lifetime. And that has been really more than 10 years of work. And these have also been validated, so certified by DNV, which is an important industry standard, standardization body. Sorry? Oh, I thought I heard the why. So these tools have been certified by DNV. In this slide, you see 4 examples. In total capacity, more than 100 megawatt has been installed. And I will not go into the details of all of these demonstrator projects, but these are with different rope designs, different water depths, and also certified by different bodies. So you see ABS, Bureau Veritas, and DNV being mentioned. And that is a very important thing, and also for future commercial scale projects. One of the things good to mention is that the Seastal project will be decommissioned this summer, and we will be able to get ropes back in order to determine what is the remaining lifetime and compare that versus the predictions. Go to the next slide. Next example that I want to highlight is offshore cranes for deep water installations. And here the advantages of Dyneema over steel are obvious. The example in this picture shows that with a 150 tons crane used to put a load on the seabed at 3,000 meter water depth, the weight of the steel cable is already taking half of the crane capacity. While for Dyneema, which flows on water, this does not impact the crane capacity. So the full rope capacity is available, the crane capacity is available for the load. And this results in lower crane and vessel footprint, so in energy saving as well. But also, since Dyneema does not rust, you don't need any lubrication, and because it's light and soft, it improves crew safety and comfort. Go to the next slide. So as you can see in the 2 pictures at the lower bottom, the rope is stored on a winch, and it runs over different sheaves from the winch to the hook where the lift is loaded. And in such configuration, the rope therefore runs over a number of sheaves, roller guides with different diameters, inducing bending to the rope. And this is what we are testing in cyclic bending over sheave equipment that you see at the top in our Global Innovation Center. Let's go to the next slide. So what actually happens when bending such a rope repetitively over a sheave is that you will create some internal friction, and that is caused by abrasion inside the rope. And this will lead to a decrease in strength, which can be observed by an increased number of loose filaments on the surface of the rope, which finally leads to breakage. And there are several parameters that are impacting this number of cycles. For example, the sheave diameter, if it becomes smaller, it is more severe, you will get less cycles to failure. Temperature has a negative impact. Load higher means less number of cycles. And also we know that the friction between the different fibers plays a role. So we have developed coatings on fiber and rope level to improve that performance. Next slide. This bend testing has generated a lot of data and has been turned into a bending tool. Don't worry, I don't go to all of the examples, but I think what is important to mention is that within the engineering, we try to be a bit conservative because we want to prevent breaking. So the dotted line in the force versus number of cycle curve is showing how normally the holding capacity or the break strength of a rope decreases with the number of cycles. And the blue line is how we look at it from an engineering point of view. Then what is important is different sheaf diameters and loads have a different impact on the number of cycles. We have found a formula giving a good correlation between these loads and sheaf diameters versus rope diameters, and that is capable to give prediction on the numbers of cycles that we will see in the application. It is also a powerful tool to reduce the number of testing that we need to do. And although I realize the picture at the bottom is small, it shows on a specific crane a monitoring system with every green part showing 1 meter of this 3,000 meter long rope, and that exactly monitors which meter has seen how many bends, and it turns from green into orange to red, so that the crane operator knows when he needs to take action and needs to have the rope switched out for a new one. And that is really installed on an offshore crane that is used in the Gulf of Mexico. Next slide. I think it is good to see that actually now 2 offshore cranes with Dyneema are operating, one, as mentioned, in the Gulf of Mexico, the other in the Middle East. And this has only been made possible due to the engineering tools in combination with certification and our efforts in the value chain. So we have partnered up with all the players, from our direct customers to the owners, to the crane operations. And that is where we are now. We are getting samples back in order to do our rope CSI to see, look at the failure mechanisms. Didn't we overlook something? Can we improve our value proposition? And of course, the target is to have more ropes with Dyneema sold in the application. Next slide, and that's my final. So in conclusion, to be successful in new applications with Dyneema, we need good teamwork. It's not only about sales, not only about development, we really need to work together. And that is up to the team in application development being out in the market to motivate and to find champions for Dyneema, research to determine and investigate the failure modes, the Global Innovation Center to actually test and build the equipment that is needed for that, and engineers to build these predictive models. Experience in the value chain influencing is important for marketing and sales and ADTS, but also knowledge on how to certify, because certification in this case is not about following prescriptive standards. It's really certifying an innovation and to convince the value chain that it's safe and reliable to use ropes with Dyneema in these kind of applications. And that comes to the conclusion, when engineered together, the impact exceeds the sum of the individual parts. And with that, I would like to close my presentation. Thank you.
Well, thanks, Judith. Great presentation and a nice example where you can see that innovation is really the engine to differentiate in the market, and that we can provide unique solutions to the market. A nice example. Moving to the last presentation for APM this morning. That's about ultra high molecular weight polyethylene, and that's our feedstock. John will give a bit of explanation what we are doing in our UH lab. John, floor is yours.
Thank you, Frank. So basically, the idea of this talk is to give you just an overview of what we do in terms of ultra-high molecular weight polyethylene, because not only do we make polyethylene, ultra-high molecular weight polyethylene for our fiber business, but we do have some excess capacity that we sell into other applications, which, with the help of Avient, we would really like to add some more value to that segment. So just as a basic background, when we talk about ultra-high molecular weight polyethylene, we're talking of something between 10 and 100 times higher in molecular weight than normal HDPE and LLDPE. So we really start at 1 million Dalton, and we range up to 10 to 15 million Dalton. That gives it some unique properties. It has a very high melt viscosity. And in certain applications, the higher, well, not necessarily for fiber, let's say high abrasion resistance and impact strength at low temperature are a critical one. But with that comes a challenge. The high melt viscosity also makes it very challenging to process in conventional terms. And also, because the molecules are so long, it's very hard to fully characterize, let's say. So you're not going to run a sec of ultra high molecular weight and expect to see everything that you should see, for example. Next slide, please. So just to give you an idea of what we're like, in Sharpie impact tests, ultra high passes all the time. We have to have a double notch impact test there for ultra high. And you see from the left-hand side that the peak in impact strength comes around about 1 million. So we have a low molecular weight, low impact strength, around about 1 million we peak. And then after that, we drop off. And that's because we're moving from different fraction mechanisms. The graph on the right-hand side shows you that even with a double notch impact test, you still have impact strength down to cryo temperatures. So this is why you see like liquid nitrogen dewars with white ultra high linings. So it still has impact strength even at cryo temperatures. Next slide, please. Another big value proposition is the coefficient of friction and wear resistance. So the combination of wear resistance and coefficient of friction allow a lot of different applications in where parts are moved across surfaces, let's say. So that's also the three main, let's say, properties of ultra high that sell in our non-captive business. If I can move on to the next slide, please. So this just gives you an idea because we don't form films in the normal way. We don't extrude in the normal way. Basically, we make ultra high, and depending on what you want to do in the end application, we either ram extrude. Injection molding is for very low molecular weight, high molecular weight material. But traditionally, it's mainly sintering, where you compression mold or ram extrude, and then you machine a part for different applications, depending on the combination of things. For example, pumps for chemical plants typically have gears made of ultra high molecular weight polyethylene because wear, friction, and also chemical resistance, high chemical resistance. There also on our side, we're mainly focused on gel processing. So our fiber spinning is basically a gel processed material. The other big gel process material are things like lithium ion battery separator films. And a growing interest is in what's basically compounding ultra high molecular weight into engineering materials, either to improve recyclates properties or to basically add wear and friction to an engineering material. If we want to step one more forward, please. Just to give you how we basically approach things from an APM point of view, basically, we look at things in length scales. So if a problem or an opportunity, we first try to fix it at the continuum or the macro level. For example, if we're looking at a new rope, we'll first have a look, what can we do in braiding? What can we do in that sort of thing that doesn't mean starting right at the bottom with molecules. So this is how we approach a problem. It's only when it gets to the bottom where we can't solve it any other way, do we start looking at the molecules. So for us, if we need to do something from the UH group, it's because it really can't be done any other way. There, and that's the advantage also of being backwards integrated. We can make the molecules that will make the morphology and get what we want on a macro scale. So if we go to the next slide. So basically, we design UH in 3 different axes, let's say, or we call it R3Ms. Microstructure, that's basically how long the molecule is, what sort of side chain branching there is, even down to end groups. What we call modality or distribution, and it's going to either be via molecular weight or chemical composition. So where are the branches? Are the branches in the high end? Are the branches in the low end? And then because our product is, our final product is not a pellet, it has to be delivered in a form factor that fits downstream processing or the application that people have in mind. So as an analogy, if I can have the next slide, please. You know, from microstructures, we sort of design the flavor. We combine those flavors to a blend. And then all of that flavor and blend needs to be in the right size grain for your equipment. So the grind, that sort of coffee grind, that's basically an analogy of how we design things there. For certain applications, you might need a smaller particle size. For certain applications, you might need a higher particle size, for example. If we can have the next slide, please. So how do we basically control it? So basically, we control it via a mixture of understanding catalyst technology, but also polymerization technology. So we can design the perfect catalyst that has great DNA, but if we put it in a poor environment, it's not going to make the product that we want. So what we do within the group is basically bring together the knowledge on catalyst technology, and process technology to be able to make these, or to be able to design in these 3 axes there. And that's basically the core of how we pull on the strings to design things. If I could have the next slide, please. No. Sorry, there was an animation in that one. So what we have basically in our lab, we are very fortunate to have basically from explorative to pilot in one lab there. So if you look at it on an explorative scale, we have what's called a 2-liter reactor where we make 200 grams of polymer per batch. Anything that's very new, we usually try in this one because if we make a mess, it's easy to clean and it's harder to clean in scale, let's say. So everything that's not known is tested out on this. And here we have the ability to look at co-monomers like propene, butene, and higher alpha olefins there. Also with hydrogen to regulate the molecular weight. And we have a fairly broad window of operation from 0 to 90 degrees C and from 0 to 12.5 bar gauge of ethylene. The next step up is our development reactor, which is a 10-liter reactor, which basically makes 1.8 kilos of sample. This already at this size is fully translatable to our plant. So what we can make in here, we can make in the plant, more or less, there. And what we do in here is where we're developing things for understanding responses and things like that. And then when we finally tune into what we like to produce, then we move to the 55 liter reactor, which makes about 9 kilos of polymer. And this 9 kilos of polymer also is enough to feed our fiber spinning pilot lines as well. So that's basically what we have in terms of capability, and we have quite a lot of there's quite a lot of things that we can do and try that is not normal as well in these reactors, let's say. If you want to go one slide further, please. These things are also fully automated. We do this also to reduce the exposure of our technicians to chemicals, but also once it's fully automated, we can get as much information from each and every reaction. So not only do we do the analysis on the polymers, but we can follow full kinetic data and predict how we can adjust our temperature control, for example, or where are we reaching our problem with cooling, where are we reaching our problem with stability in a larger process. This can all be mapped on our 10 liters and 55s before we go to the plant. And in this case, we were much faster to translating from basically bench scale to plant. We're less likely to make failures, let's say, because if we make a mess in the large plant, then it's 4 or 5 days out of production. So nobody likes to let us in there if that's what's going to happen, let's say. So we tend to fail fast on these reactors to not fail on the larger reactors. If you could go one more, please. We also back this up with quite a lot of analytical tools that we have in-house. Basically, for molar mass, we measure what's called elongational strength, which is basically like a melt indexer for high molecular weight polymers. We also have IV, secmols, and we have developed solution rheology, where we make a dilute solution and do rheology on a dilute solution of UH. To understand molar mass and molar mass distributions and so on. So we have access to quite a lot of things. There are a few things that we still would like to understand, and that is cross-linking. How do you measure cross-linking in gel formations and things like that? And I know with Chris, we've had some talks on that side of things. If you go one more. We're already starting to work with an Avient. We have a sampled material, our standard commercial material, which we haven't optimized. It's just what was on the shelf. That has gone to the Global R&D Center in India for sound dampening. Claire has been looking at it for as an additive to improve mechanical properties, and then we've also sampled it to CycleWorks for adding to basically buy back the properties of the recycler that is sort of degraded along the way from an additive point of view. So we are already in working, but we would like to discuss with anybody that has or sees a potential for other areas that we could go into with this. As you say, we're quite flexible to design things and sample things, and I think that the size that we can sample is also relevant, because two polymerizations is the equivalent to a 20 kilo bag, more or less. There. And I think, is there one more slide left? Yeah, no. That just shows you some of the various things that UH can do. And I think with that, it's just, if anybody wants to get in touch with us, we're more than happy to discuss what you could do with UH or what we could do to help you do something with UH. Thank you, Frank.
Okay, great. Thanks, John. So these were the 4 presentations from APM. Yeah, thanks for your attention, and hopefully, you get some inspiration for applications in fabrics and composites or new ultra high molecular weight polyethylene applications. Please reach out to us so that we can really try to make that happen and become successful broader in our industry. Okay, back to you, Phil. Thanks.
Yep, Frank and team, it was great. Meredith, you got a ton of ideas. I hope you're ready. There's all sorts of people that jumped in with ideas for you, so that was a great ask. And thanks to Hans and Raul and Judith and John. John, really nice to see the collaboration. I'm familiar with a number of those projects, but it's great to see the connection across business units. So thanks for that, and then just well done to the APM team. Really appreciate that. We know that there's some sensitivity sharing some of the key aspects of the technology. I think you walked that line quite well and still made it accessible for everyone. So really appreciate the contributions. Michael, Adam, are you on?
Yes.
Oh, great.
Yes,
I know you
I'm there.
you had a number of commitments this morning, so thank you for adjusting your schedule.
I'm jumping from one meeting to another, trying to accommodate and please everyone. So I'm just back on time. So are we going straight away, or do we make a break, or are you introduce?
Yeah, unfortunately today we don't have time for the break. People
Okay,
will just
fine.
have to do what they need to do. But yes, we'll go straight away.
Okay, thanks. So hi, everyone. So I'm pleased to introduce the last 4 topics and speakers of that wonderful 3 days of Technology Wolfpack. And those last presentation will tell a consistent story of how we, as a team of Avian, create value to translation needs into scalable solutions. So you will see across those projects that you will see the same pattern emerging. We start from obviously unmet customer needs. We leverage our unique technical skills and global capabilities, and we translate them proven ideas into solutions that can be replicated, scaled, and commercialized across region and application. So whether it's going to be application replications built on validated successes by Brad Davison, or breakthrough formulation and processing expertise deliver cost-effective pigment dispersion by Pauline Martinet, or regulatory-ready solution for demanding appliances market by Mehmet and Laura with the 5 VA-rated flame retardant grades, or the last advanced material responding to evolving healthcare trends by Jao. Each of those projects demonstrate how we combine innovation with execution. So together, these examples you will see show how we turn technical excellence and collaboration into real, repeatable impact for our customers and Avian worldwide. And now I leave the speech to Brad that will talk to nice replication, translation opportunities.
Wonderful. Thanks, Michael. Appreciate it. Good morning, good afternoon, good evening, everyone. Before I get into this particular topic of application replication, I wanted to say that, first, following Dyneema is a tough act, right? I think they do some fantastic work. There's a lot of things that we can look at from a different business units and what we can do with that particular product, but also they've already demonstrated quite a bit of replication in their product lines. You've seen all the different areas where they've taken their unique solution and have applied it in a variety of different ways. So this is nothing. What they've been doing is what we're going to talk about here a little bit more in depth, and then just show you the journey we're taking within particular business units on how we're going to identify ways that we can replicate success, if you will. So next slide, please. So I wanted to figure out, like, what is replication here? What are we even talking about? And this is something that, not to steal any thunder from the town hall today, but you will hear about some of this as well. But basically, if you think about it on a DNA level, what does it do, right? It copies its information before it divides and creates more. And it's similar to what we're talking about here. We're looking at taking information that we already have, that we've already derived, and how can we copy that and then put it in different areas, right? So this will help us look at increasing speed to market, basically. And that's something that Dave Schneider had mentioned when we talked about this, is how do we take our known solutions that have solved a problem, a known problem, take that and then proliferate that throughout the markets or to different customers, markets, and/or regions. Next slide, please. So one way that we've identified to do this is by looking at what's known in our business as RCRs, or rapid customer responses. These are actual programs that come in more of a proactive development more of a reactive development than proactive, where customers come to us with a particular problem. We need this, or we want our product to do that, right? And based on these RCRs development, which are typically shorter time period than what you see with an MPC1 or MPC2, is we have direct VOC from a customer, right? They are coming to us and saying, I have a problem, help me solve this. And the result of an RCR development can be a new solution that we hadn't considered before. It can be a slight performance tweak to improve upon an incumbent's material to be more competitive. slight changes in differentiation or to fit the application, like I mentioned, or even cost down formulations. So RCRs are actually fairly broad. But if you consider some of the discussions that we had, where we recently heard from Nike, innovation can be of any size. For Nike, a color change on their applique is a huge innovation. So it doesn't always have to be a brand new, formulation that we put out there. It can be something that we've done differently than the market has done. Next slide, please. So when we look at RCRs, we're thinking, okay, we can't do it for every RCR we do. I mean, currently in SCM North America and Europe, 70% of our business is RCRs, right? So we do a lot of different things for a lot of different customers. What we try to do is understand.
Yes. Okay.
Sorry?
Yeah. Okay. Thanks, Hans.
Yep. Somebody's not
Thank you.
muted.
Yeah. Thank you. Well done.
Okay. So we look at our RCRs and decide, okay, how can we look at these in a different scope? How can we look at these and derive this is an RCR that we should look at replicating? So what we've done is we've derived a way to try to score these RCRs in a very quick way. That doesn't mean that some RCRs that score low may not be considered, but it's at least a starting point when you're talking, potentially hundreds of different projects that we're working on. So we want to look at, is this a new application to either Avient or to the industry, right? Is it a unique technology we've derived? Can this technology be protected? Is it something that can be trade secret or IP protected that may give us a differentiation or an edge? And also time to implement, right? Was this, for instance, solving a regulatory need that has already put us ahead of our competition potentially? So once we'll do that, the team will go through, and this is a team of the ADTS, the product development team, et cetera, will review this and determine, hey, we think we have something here. We think that this application that we derived is unique enough that it might work for other similar applications within a customer or within a market, or because of the performance of this, it could work in several different markets or even regions. Once we have done that, we then put it into the scoring, and then we go review that. So next slide, please. So this just shows an example of what we looked at within SCM North America, and we even drove it down even further to look at healthcare market, for instance. And we tried to say, okay, based on that criteria that we had set out, as rudimentary as it is there anything that floats to the top? Is there anything that we should really look at here? And for this example, as it shows, this tubing mandrel that we looked at using a TPE material from our GLS technology had something unusual, right? It was a new application either to us or to the market that hadn't been done with TPE before. It was a new technology that we derived, and it was protected. Now, was it regulatory driven? No, but it was still something that came out and said, hey, this is unusual. But what I want to highlight here as well is that even though something might come in at 8 or even a 4, does not mean it's not replicable. It just means that we're going to look at something that has higher potential first, and then we'll come in and look at some of those secondary areas as they become available to us. Next slide, please. So once we've, as a technology team, have gone through this, identified these, right? We then want to partner with our commercial teams and our marketing teams, say, hey, this is what we think. Is there really something out there? So those other teams will take it and then decide and do a deep dive for us, understand, yes, there is a market potential. They will build customer lists, for instance. But more importantly, we want to understand how can we then demonstrate this material's performance for that market. So we'll then go and look at ways that we can characterize the material for different analysis for a customer. What type of market data can we then produce and provide for our customers? And also as well, what type of demonstration pieces or samples can we give them? Because many times walking in with a data sheet, for instance, or a tensile bar is not really going to tell the story. But if we can provide something where the customer is tangible, they can put it in their hands, go, oh, wow, yeah, I really do like this. Now they can understand why we've come to them with this particular technology and how it can be of value to them. Next slide, please. So in this journey thus far, we've identified within the SCM Atlantic business 3 different areas to pilot. Obviously, the first one is a VersaFlex thermoformable TPE, and I'm going to talk a little more in depth about that. The second one is a VersaFlex wet grip TPE, and these are TPEs that even when they get wet, they retain their grippy performance capability. And then finally is our Maxim FR5 VA material, which is the next level in flame retardancy used for, as shown here, appliances, for instance. Next slide. So we wanted to go through, and this is a great example of something that was unique within our TPE business, that we were able to solve a problem for Tesla that can then be put into their semi-truck. So what we've created, it's an anti-stat material. It's a TPE-based product. abrasion resistance, etc. But what really makes this a little bit more unique than just those performance criteria is its ability to be extruded very nicely into sheet and then be thermoformed, as the picture shows on the bottom, into a very intricate shape that then fits a customer application. Typical TPEs will not be able to survive some of the undercuts in different areas during thermoforming. They'll stretch, they'll tear, they could bubble. But in this instance, the team came up with a fantastic solution that has the melt strength, has the retention, the capability of being formed into this shape and still survive. And we also looked at some of the feedback that we have gotten on this particular program to show that not only did it perform as we expected it and it performed well on the processing side, but the VOC that we then received from customers, such as the extruder, was that this material runs great. There's something truly unique about this that allows it to be extruded well. We want to look at it for other applications. So when you start getting that kind of feedback from processors, the light bulb goes off and we say, okay, if this stuff extrudes so well, where else can we put it into extrusion applications? We know it thermoforms very well. Where else can we put it in thermoform applications? We know it's being used in an industrial application, or in this instance, a heavy truck application. How else can we proliferate this within that market and then also cross markets? So some of the added benefits of this particular one was that, like I mentioned earlier, the anti-stat performance, which allows it to stay cleaner longer. It's not going to attract dust particles, etc., given its performance capability. And with this one thus far, we've had commercial product already. They've already built trucks to be used in the market. They've actually, because of its performance on the inside of the cab, they've looked at extruding this for steps, for instance, and grab handles as well. So we've seen the performance of this product already spread throughout this particular customer. Now we're looking at how can we make that broader, either within region, across market, what have you. So the next steps in this particular pilot is to develop that customer list, which is in progress, create a host of internal training, which we're doing as well. And then we're also looking at creating those prototype parts to be able to demonstrate performance to a customer. So we have within corporate R&D, they have a thermoforming capability we're going to investigate. We're going to look at printing tooling to go in that unit to really demonstrate the way this material performs. And it's all in a push to demonstrate performance, to get out in front of a customer with a known product solution that we can then very quickly get out to market. Next slide, please. So I've gone through this rather quickly, but I wanted to go through and at least highlight what does it take to get a project from understanding of it being a replication potential all the way to doing it. And this just gives you an idea of the timeline to do something like this. So again, won't do it for every RCR that's out there. We want to make sure that we understand what problem did we solve, how did Avient win, and how can we take that solution and then again proliferate it. So like I mentioned with the Tesla example and the other two pilots that are in place, we're at the point now developing the application package for sales professionals, and then we're going to be launching that here in July to get that out into the market. And then at that point, we can start measuring success. We'll have a campaign towards it. Any new opportunities that come in, we've measured against that. And our goal is to have 3 closes within this year with a replication potential. And I think that's it. Next slide. So if you have any questions or if you're interested to know more about how we're progressing through this, please reach out and let us know. As I mentioned earlier, the Dyneema business has done a very nice job of taking their unique solution and proliferating cross-market that we've seen with defense, marine applications, and consumer applications. And that's my time. Thank you.
Hey, Brad, thanks a lot for your contribution. I just want to make a quick comment. Normally I don't, but thank you for that, and really appreciated the process you walked through, almost like a real win worth with respect to identifying, replicability opportunities. Garland had an interesting suggestion yesterday to a question I asked in the chat about working groups, and he identified one that's maybe more generic around or broader around application engineering. Maybe reach out to him. I'm sure it's an idea that you have too. There may be an interesting opportunity of how we come together as a company in a working group in the area of application replication and application translation. So thanks, Brad.
We'll do that. Thank you. Thanks, Phil.
Thank you very much, Brad. So let's move now to the SMASH technology, and Pauline is going to talk through what that means and how it can be also contributing to being translated in other parts of the world.
Yes, thank you. Hello, everyone. I'm really delighted to have the opportunity to present the SMASH technology to you all today, a project we are working on since 4 years now with Jordi Rigouan, Caroline Marchand, Stéphane Rousseau, and others. Next slide, please. So let me start with a challenge any color master batch producer face, the pigment dispersion. Dispersing organic pigment is a difficult task because pigment particles show a high tendency to agglomerate. As a result, we obtain a poor dispersion quality, as the pictures show in the right side of the screen, where we can clearly see some pigment spots. In the left side of the picture, we see a deep and intense blue surface with no pigment agglomerates. And at the end, the dispersion is about avoiding those agglomerates in customer end products. This is a key factor for processing and quality performances, which can easily drive cost up. And this is particularly important for us because of our SPD portfolio, so for which we produce more than 1,000 tons a year that end up in more than 5,000 custom formulation representing 50 million turnover. Next slide, please. Historically, we relied in two main technologies to disperse organic pigments, both quite simple in formulation techniques, mainly driven by PE wax or wetting agent, but with complex processing. The wetting agent technology uses PE wax emulsion that brings a high amount of water into the extruder, where we need special equipment to remove the steam afterwards, like long extruder or side vent stuffers. In the other end, the hot-cold mix technology uses solid PE wax and a complex mixing process to melt the wax. It requires specific and low productive equipment due to long mixing and cleaning times. So we knew we needed a better way, and that's where the SMASH comes in. Next slide, please. So what was our target then? So we want to develop a formulation and a manufacturing technology to disperse 40% organic pigment at excellent quality from film and fibers and top throughput for polyolefin carriers. Additionally, when we asked for VOC and VOB, there was a clear need to reduce costs, to improve the regional manufacturing flexibility of the SPDs, and also reduce the dependency on PE wax as dispersing agents. Next slide, please. In terms of formulation, we use the wetting agent technology as a starting point. The water contained in this technology plays a key role when it comes to dispersion but we knew we had to decrease this amount of water to gain in equipment flexibility. So to reach excellent dispersion properties, we first need to wet quickly the pigment and to densify the mix to allow good feeding of the extruder and ensure a high output. This is done by the water contained in the emulsion, but to reach high level of dispersion, we need also to optimize the interaction between the pigment and the water. So we looked at the chemistries that allows this when balancing with the amount of water, and we took the direction of surfactants, playing the role of synergist between pigment surface and the wetting agent. A lot of different surfactants have been tested, and with more than 100 extrusion trials, our improved formulated solution contains now standard PE wax, a water emulsion that complies with all our regulatory requirements today, and ethoxylated sorbitan esters mainly as a synergist. Next slide, please. So this is what you can see here, the standard SMASH formulation for organic pigment SPD, with the water-based emulsion to boost the dispersion and with the Sabofog to optimize the interaction between pigment and water. And this boost is quite mandatory for very complex pigment as copper phthalocyanine, for example. You can see the molecular structure on the screen of the pigment. On this particular pigment, the presence of nitrogen atoms contribute to the polar portion of the molecule, while the hydrogen atoms of the benzene rings are highly nonpolar. Thus, the copper phthalocyanine molecule consists of both hydrophilic and hydrophobic areas. Next slide, please. And this is the case also for the surfactant. It has a hydrophilic head and a hydrophobic tail. That's why it will play the role of the synergist between the polar part of the water and the non-polar part of the pigment. The main characteristic of a surfactant is the HLB value, means the hydrophilic lipophilic balance. The scale is defined from 0 to 20, as you can see on the table, and the Sabofog has a value about 11. So this is right of the middle of the scale. This means the balance is almost a 50-50 between the polar and the non-polar part of the surfactant, and this is ideal for the polarity of a wide range of organic pigment. We also tested other surfactants with other HHB value, but it did not show any dispersion improvement in our process. Next slide, please. In addition to the surfactant testing, we used some statistical tools as well to fix the better ratio between the PE wax, the water emulsion, and the surfactant. The output is the pressure in that case. So I mean the dispersion result via the filter test. Here, these are two different views showing the same results. But if you look at the 2D representation in the right side of the screen, you can see that the lightest area means the lower pressure. So the ratio has been fixed based on this. And we know this is working pretty well for a wide range of organic pigment. And we know also that we can increase a bit the amount of water emulsion for very critical pigment, but still without using any specific equipment to remove the steam, like the vent stuffer. Next slide, please. We all know that we need mechanical work via extrusion to disperse a pigment. So here is how it works. The water of the wetting agents wets the pigment particles, increasing the bulk density and enabling an optimal feeding into extruders. The surfactant creates a steric barrier due to polarity differences between the water, pigment, and polymer, and these prevent the agglomeration. Finally, the extrusion process is designed to evaporate the steam and break any remaining agglomerates. Water in an extruder can be confusing for those who do not know the technology, but this is really beneficial in the process to adjust the viscosity of the material and also to boost the productivity. Next slide, please. So what's great is that Smash achieves optimal dispersion using standard mixing and extrusion equipment already available at Evian. No major investment needed, no complex retrofitting. High-speed mixers and container mixers have been validated. So the mixing time and the cleaning time is significantly reduced compared to the hot cold mix technology. And in terms of extruder, shorter extruder shows good performances today. No vent stuffer required anymore. Just an efficient vacuum system is needed in combination with the right screw design to reach the optimum dispersion level. And for some pigments, we almost doubled the output. So it won't be the case for all pigments, but this is really promising and it could give a real value to this new technology. For sure, there are some adjustments to be done versus the hot cold mix extrusion process. We need a more aggressive screw profile. We also need a lower temperature profile. We need to increase the RPM, lower the feed rate to induce even more shear to the material. But that's something manageable. All the plants producing today with the wetting agent technology should be able to switch quite easily to the Smash. And we had the confirmation here on our plant in Assès in Belgium. And via several industrial trials, we also demonstrate then that the hot cold mix expert plants like Lomagna in Italy or San Andreu in Spain are able to produce Smash as well. At the end, all these achievements can also be translated into numbers. So the manufacturing cost reduction and the energy consumption trigger 50% of conversion cost reduction. Smash protects our core. We produce around 1,000 tons of organic SPD annually, and this would represent $500,000 of saving per year in Europe. We need to innovate here to outpace the competition. Color is the easy part to compete, but transforming our way to produce will generate better output, better quality, and this will be reflected into better price and better processing for our customers. This will protect 50 million of existing business. Smash doesn't just solve a technical problem, it delivers a strategic value as well. It enhances the regional European flexibility via the use of standard equipment, and this is globally transferable. It supports business growth and it opens doors to new applications and portfolios as well. And we are already working on an extension to critical dispersion polyolefin powder colors. Next slide, please. It will be the last one. So to conclude, I would like to share where we are today. The technical part is now under control and we are starting the customer validation phase. I won't enter into details on this, but I would like to highlight that the hidden part of the iceberg would be the implementation when everything is approved. Indeed, the Smash SPD formulation is different from the alcohol mix formulation that is used today. We are adding some additives, means adding new cast number, potentially SML and dual use additives compared to what the customer is using today. If we follow the rules, it would mean we would have to create new product codes, would mean new validation and customers and so on. And knowing that 50% of our color portfolio is dedicated to highly regulated market segments, this represents a lot of work. But we have a chance that all these changes could be drowned into the 19 amendments change environment, so it can be the right moment to change. But that's not my decision. So the next step and implementation strategy will be discussed with the top management in the next future. I would like to finish with a finger crossed, and I hope we can implement this quite soon. So thanks a lot for your attention. And if you have any questions or need more details, please reach out to me or Jody Rigrant, for example. Thank you.
Thank you very much, Pauline, for highlighting the work you are doing and the potential benefit for the group. And now I encourage Mehmet and Laura to go through the topic of 5-year rated flame retardant grades for appliance market.
Yes, thank you. Good morning and good afternoon, everyone. Today we want to share our work on especially PP-based UL94 5-year rated flame retardant solutions for the appliance market. Actually, this project was started 2 years ago, and now it is a good opportunity to share technical details with you. Today, I am Mehmet Güçlü, together with my friend Laura Carlizo. We will try to explain why this requirement became so important and what technical challenge it created for polyolefins, the solutions and Evian has developed, and how we managed to attract our customers. So let's start with the strategic importance of this topic. Next slide, please. Yes, the trigger was the tightening of refrigeration safety requirements after the Grenfell Tower fire in 2017, and which had unfortunately 72 fatalities. Following that, the related ISC standard was published in 2020. And its implementation became mandatory in September 2023. And the practical result is that the appliance in insulation should be a metal or a 5VA based polymeric material. This change created a very strict rules need for new polymer backplate solutions and with higher fire performances. And it is not only a safety requirement for refrigeration, but also it became a preferable solution for other plastic parts of household market. So the question became, what exactly is the problem, and what we need to solve for appliance market OEMs. Next slide, please. What problem are we solving? OEMs need fire-safe polymer solutions that can replace or reduce metal without sacrificing usable internal space, with lower cost, easily moldable materials, and of course with long service life. Moving from metal to polymer gives more design freedom to us, but as soon as the compounded polymer can meet the new fire requirements. So the problem is not just a flame retardancy. It is bringing, with this, it is bringing a practical appliance solution with the right balance of the fire, performance, thickness, and manufacturability. To understand why this is difficult, we want to explain what 5VA actually means. Next slide, please. What is 5VA? And the name of 5VA is coming from the test, actually, which is 5 times 5. I mean 5-second contact with flame and then 5-second rest. 5VA is one of the most severe UL 94 classifications because it requires a successful performance in the bar test, but also in the plug evaluation, it is also important. It is not enough for the test bars to self-extinguish. Additionally, there shouldn't be any hole formation in the plugs. So when we say 5VA, we are talking about a much tougher requirement: no cotton ignition, no long after flame, and no plug formation. In the right side of this slide, you can see some plates with some hole formations on the middle of the plates. These are not okay parts because the standard can allow the dimension of the holes up to 3 millimeters. To work on this, we needed internal capability for proper testing. Next slide, please. To support 5VA emission and to improve ourselves, plug geometry, molding conditions, and the test chamber is the main parts of proper testing. For that reason, firstly, we invested in a 5VA plug insert for 1.6 millimeter thickness, which is the most common reference for flame resistance polymeric materials. At this step, thanks to US team, because they supported us very effectively in testing our samples as an accredited laboratory. For Istanbul plant, a new UL 94 test chamber is planned to be activated within this year. Now let's talk about what are the technical challenges we faced during this project. Next slide, please. Achieving 5VA in an unreinforced PP is not only a formulation problem, it is a combination of FR chemistry, matrix interaction, and processing. Internally, we saw that the thin wall stability depends on the FR type and loading. During our works, we saw that PP copolymer showed better dispersion than PP homopolymer, and that higher viscosity PP performed better than lower viscosity because of the dripping effect, of course. Since these NHFR systems are sensitive to shear, and temperature. We prefer a low temperature profile and a proper screw design for our future plans. So the challenge is really in chemistry, resin selection, and process discipline. At the end, what is our current system? Next slide, please. Our current technology, our development is based on halogen-free interluminescent system with char-forming behavior, using a phosphor nitrogen-driven approach for polyolefins, especially for PP. Since our customer requests are coming us for non-halogenated systems, we tried different NHFR systems and saw that depending on the customer process, the color of the parts, the wall thicknesses, the geometries, and the volume of their machine can affect on the performance of the materials. So these items directed us to use different combinations in different formulations. So currently we have a set of solutions for several customer requirements. And now I am leaving the stage to my colleague Laura Callizo. Thank you.
Thanks, Mehmet. So next slide, please. So in this slide is an overview of our current 5BA portfolio, but the key point is that these three grades do not have the same positioning. The one on the right, for example, the 1510 is our most mature solution. It's 5BA at 2.0 millimeters. The UL listing is already completed, and it is also PFAS free. The one in the middle, the 1508, is our second commercial route. It is also 5BA at 2.0 millimeters, and the UL listing is ongoing currently. And the last one, the 1509, is the really strategic one, because in this grade, we are targeting thin wall at 1.6 millimeters. The situation with this grade is that the scale up is already completed. We obtained 5BA on the lab light sample. So what we are doing now is confirming that the same performance on the scale up material is similar to the one on the lab, with the 5BA testing that is currently ongoing in Avon Lake. UL for this grade, the UL listing for this grade for sure has not started yet, because we are waiting for those results. But what it is important here is that these three grades cover different maturity levels and different customer needs. Overall, the portfolio already gives us two credible 2.0 millimeters routes today, while the 1509 is the program that could extend us into the more demanding thin wall space. So beyond these grades themselves, the next question is, why are we in a strong position to convert this portfolio into real business? Next slide, please. What is making the difference for us is not only the material itself, but the way that we are supporting the customer from development to industrialization. Because we have already real solutions moving into the market, but at the same time, we are able to react quickly during validation, during the scale up, and during supply discussions. And that really matters, because in those type of applications, customers are not really only choosing a formulation, they are choosing a partner that can help them move fast from testing to implementation. So our advantage really comes from combining, from one side, the technical credibility, and from the other side, the execution speed. Next slide, please. Well, this program is already moving beyond technical validation and into the early commercial traction. And importantly, this is linked to real applications, as you can see on this slide. It's not just a general customer interest. The one on the left, Arcelic, the grade choose was the 1508, is validated for a refrigerator chassis application. We have already delivered 10 tons year to date, with a forecast for 2026 of 60 tons. The other project for Ser del Bora, in this case, the grade selected was the 1510, is validated for a fume extraction application. There, we have delivered already 26 tons year to date, with a forecast for this year of 250 tons. And we think that the applications themselves are important, because they show the breadth of the opportunity. On one side, we are in the classical appliance structural component, like the refrigerator chassis. But on the other side, we are already engaged in a different use case, such as fume extraction, which shows that the platform can go beyond one single part design. And moreover, we have those two cases, but we are also engaged and targeting key players, like, for example, BS8, Samsung, Electrolux. So this opportunity is no longer theoretical. It is already linked to concrete applications and active customer programs. And to make that possible, a strong execution across the teams and sites was essential. Next slide, please. So one point that we really want to highlight is that this program was not really only developed by one person in one site only. It was built through very close collaboration across multiple locations, each one contributing to a different part of the work. So, for example, sample production was mainly done in Barbastro and Istanbul, but we have additional sample production also in Mele. The scale-ups were carried out in both Barbastro and Istanbul, but for example, for 5BA molding and testing, Avon Lake play a key role, while there was also some 5BA testing also supported in Gaggenau and Istanbul. So you can see that there was a cross-site collaboration. And this was important not only for the speed of the project, but also for the confidence in the data. Because when you have mold, sample production, the scale up, the 5BA in different areas across different locations, it allows us to cross-check the work, to de-risk the program and to move forward with a broader technical database. So this is really a good example of how combining capabilities across sites allow us to move faster and progress the program from development into customer validation and commercialization. And from here, the next steps are clear. Next slide, please. As mentioned, the next steps are clear. So we need to complete the IP review. We need to confirm the data required for the launch package. We need to move through the go-to commercialization gate review, and it is needed to prepare the seller training. In theory, all those actions should take place during this quarter. So in the coming months, everything should be over or ongoing. So in parallel to those actions, we also want to strengthen the flammability testing capability that we have in Europe, including the UL94 cabin upgrade in Istanbul that my colleague Meme commented. And we also are planning or looking to expand the molding capability in Gaggenau and Barbastro. So as you can see, this story is clearly not finished. We already have early commercial traction, and the focus now is to industrialize the solutions. We need to strengthen the capability base and grow the platform. So the next phase is really about turning what is already a technically and commercially credible program into a broader and more scalable platform. Next slide, please. So with that, we would like to thank you for your attention. And just to remark one more, that for us, this program is a really good example of the One Avian in practice, because I mean, different times and sites working together to turn a technical development into a real commercial opportunity. So thanks again, and we will now be happy to open the floor for questions or in the chat, or we can connect separately later. Thank you.
Thank you very much, Laura and Mehmet, for that nice piece of work with that global collaboration. And I suggest we move to the last presentation of the day, and that will close the 3 days and intensive and very valued time on Technology WolfPack. So color chromatic presented by Zhao will talk about the item biocompatible color range called Transcend. So Zhao, the floor is yours. So we don't hear you. I don't know.
You're not gonna mess me up. Trust me, that's what I turned over. That messed me up. This. Okay.
I don't know if we can unmute Joe, or do you have any issue particularly? Are you online?
Looks like They're unmuted. I wonder if there's a connection error right now.
Did you try to text directly? Yeah,
I will.
you are. I'm gonna do the same.
She connected.
Looks like yes. Amazing. We haven't had any kind of issues until the very last one. Let's give Joe just another minute. Thanks everyone for hanging in there.
We should take it as a positive sign of, this is to be continued.
Yes, that's right. Yeah, it's a cliffhanger, right? Sort of like in a TV series.
Yeah.
Phil,
Unless
did you have
Michael
any?
Adam wants to cover it.
Yeah, I was gonna say, Phil, did you have any closing remarks you wanted to squeeze in right now?
I did. And so we can't reach Joe.
It shows she's presenting, so I don't know if maybe
Wow.
she's on a different call. She's on Do Not Disturb.
Okay, well, I guess we'll wrap up here. Let me just thank all the presenters for the content and for staying on time. Just unbelievable. I just can't believe how well people hit their time marks, and there was so much content that we needed, folks to do that. Thanks also to Adrian and Jerry for bringing in the external speakers. That was really appreciated by everyone. Thanks to the session chairs. So I mentioned on the first day, and to Nicole Moran. Without her, this would not have run smoothly. I know there was some prompting of the speakers in the background to make sure that everybody stayed on time. So thanks, Nicole, as always. Amazing job. And then thanks to all the attendees. We had 400 to 450 every day, and there was really very little drop off. And so we know that this is an investment. I hope you got a significant return in that. We'll have this again in the fall. And for any of you who would like to speak in the fall, please reach out to your leadership team, and we'll be sure to get you added. And then that's where we'll end. That's a wrap. So 3 days, and really appreciate the time. And if you have any suggestions for things that we can do to improve in the future, please reach out to me, to Nicole, to your leadership. We want to continue to improve. I think this went very well. I had high expectations and they were exceeded. So, but I'm sure we can be better. So please reach out with any suggestions that you have, and enjoy the rest of the day. Town Hall will start in 27 minutes. Okay. Thanks, everyone.
Wonderful. Thank you.
Everyone.
Bye-bye.